My lesson objective is lesson 1.9, which states that the student should be able to predict and or justify trends in atomic properties based on location on the periodic table and or the shell model. There are a few main terms we have to define for our learning objective. First, let's discuss ionization energy, which is the minimum amount of energy required to remove the valence electron of an isolated neutral gaseous compound. The second is atomic radius, which measures the distance to the center of an atom. Finally, electronegativity, which measures the tendency of an atom to attract electrons. There are many science practices we're going to be observing in today's project. The first would be using models, which we are doing by using the shell model to show periodic trends throughout the periodic table. The second would be calculating effective nuclear charge, because we use that to justify how we show it on the shell model, which is how we prove many periodic trends. We will then use scientific explanations like effective nuclear charge, which we will implement in our shell model to explain periodic trends. Our 3D model relates to our learning objective by showing the Bohr shell model, which is what we're supposed to use to show periodic trends in the future. The model is 3D because it shows each consecutive shell popping out of the paper, and the Bohr model is supposed to represent a proper atom. All of these periodic properties will be observed by comparing beryllium and sodium. With that being said, let's discuss atomic radius. Because Na plus is one period higher on the periodic table, it's most likely going to have one more shell. And because it has one more shell, it's most likely going to have a higher atomic radius. It is now important to talk about effective nuclear charge, which is the net positive charge experienced by an electron of a polyatomic ion. We calculate this by subtracting the actual nuclear charge by the number of electrons. We can see that there's a higher effective nuclear charge for beryllium. Beryllium has 2 valence electrons, which means it has 2 protons, while Na plus has 1 valence electron, so it'll have 1 proton. Because beryllium has more protons, it's going to drag in more shells to make a smaller atomic radius. That's why Na plus will have a longer atomic radius, including the fact that it also has more shells. Now for ionization energy. Because beryllium is one group to the right on the periodic table, while beryllium has 2 valence electrons, Na plus has 1. That's why beryllium would rather make a shell of 8 than Na plus. That's why we would see that it would take a longer time for us to take away an electron from beryllium than it would for Na plus. This diagram would further show that it takes a lot more energy to take away an electron from beryllium than Na plus, because we would see that it's closer to an octet. Beryllium has an effective nuclear charge of 2, while Na plus has an effective nuclear charge of 1, which would mean that it would attract more electrons in the long run. B has a higher ionization because it's farther right, so it'll want to gain more electrons, and has a higher effective nuclear charge, so that means it would attract more electrons. Our final trend is electronegativity. Because beryllium is more to the right of the periodic table, that's 2 valence electrons, and it would rather take in electrons to make an octet of 8. This is why it seems harder for Na plus to take in electrons based on this video. Beryllium has an effective nuclear charge of 2, while Na plus has an effective nuclear charge of 1, which would mean that it would attract more electrons in the long run. Beryllium is more valence electrons, so it would rather gain electrons and make an octet of 8, and it's also higher on the periodic table due to the fact that it has less shells. That's why there would be more of an attraction from the nucleus for beryllium due to less shielding from their shells.